Well, you know now too.
You don't need case. There's bar in it. Okay, so last time we learned about how molecules can be polar or nonpolar based on their bonds. So remember, when you're looking at a molecule, you're going to look at the atom. You look at atoms and look at their bonds. And once again, whichever atom in the bond is more electronegative, the bond dipole is going to point that way, towards the more electronegative atom. In this case, this is water. There's a bond dipole pointing this way and a bond dipole pointing this way. Again, a bond dipole is an arrow that points to where the electron density is, the positive on the other end, and it makes a partial positive and a partial negative. Then we sum up the bond dipoles. And the sum of the bond dipoles tells us, is that a polar molecule or a nonpolar molecule? If they sum up to 0, what kind of molecule is it?
Polar.
Nonpolar. If they don't sum up to 0, what kind of molecule is it?
Polar.
Polar. Okay. Now today we're going to talk about how molecules interact with each other. And the name we give for that concept is intermolecular forces. Intermolecular forces. Inter means between, which is why you go to intramurals, not intermurals. Intra means within. Inter means between. So between molecules, intermolecular forces are forces between molecules. And the simplest type of intermolecular force is just the dipole-dipole. When you have a molecule that is polar, it acts just like a dipolar magnet would have. A north pole and a south pole, a molecule has a partial positive and a partial negative. So the partial positive of one molecule is attracted to the partial negative of a nearby molecule. Dipole, dipole. One molecule's dipole is attracted to another molecule's dipole. It's kind of like if you had water molecules, and you have, remember water molecules have a partial positive and a partial negative? So this partial negative would be attracted to this partial positive. And this partial positive would be attracted to this partial negative. Make sense? Dipole, dipole. It happens when you have polar molecules. If you have a polar molecule, you have dipole, dipole forces. Intermolecular forces. If you're with me so far, give me a thumbs up. If any part of this needs to be repeated, wave your hand around. Yeah.
So would the molecular dipole be attracted to?
Yes. Yeah. Again, the bond dipoles create the molecular dipole, and that's what we care about. We care about the molecular dipole. Because you could have a molecule that has a bunch of polar bonds that would cancel out and become nonpolar, a nonpolar molecule. So we care about the molecular dipole. Other questions? I don't know if this works yet. Seems like every time they update the computer, a little puncher has to stop. Whatever. Okay. So there we go. Now, obviously, the more polar a molecule is, the stronger the dipole-dipole force is. And we'll get into more of that later. But right now, just realize dipole-dipole, what you get when you have polar molecules. Okay. It's a fun little animation. This is a 2-atom polar molecule, kind of like hydrogen chloride. Hydrogen chloride has got a hydrogen here, chlorine on this side, most electronegative on one side, that's polar. So the chlorine on one end is going to be attracted to a hydrogen on the other end. And a hydrogen on one end is going to be attracted to a chlorine on the other end. Now understand, this is an intermolecular attraction. They're not bonded, they're just attracted to each other. So talk about what happens when they're, talk about more of that later. Okay, ion dipole attraction. We talked previously about how water molecules can come along and they can attack a lattice, like we have our sodium chloride, and water molecules will come along, and this is a negative ion, so the partial positive end of the water molecule will bond to the negative ion and take it away. And the partial negative end of the water molecule will grab the positive end and take it away. That's called ion dipole. It is an intermolecular attraction because it's between things. So that's called ion dipole. When a polar molecule, like water, breaks apart an ion or an ionic lattice, That's ion dipole. Now, the reason this is here is because sometimes some things that are ionic dissolve and some things don't. If the ion dipole attraction, listen carefully, if the ion dipole attraction, like our water molecule, oh, partial positive attack, partial negative, woo! If the ion dipole attraction is stronger than the ion attraction, the substance is going to dissolve. Sodium chloride is a great example of that. We know sodium chloride dissolves really well. But if the ion dipole attraction is weaker than the ion attraction, the molecule stays, or the ionic lattice stays together. So if water molecules like, oh, look at negative. Hey, I can't, it's like, nope, my attraction for the positive ions is too strong. You can't pull me apart. That's going to be an ionic solid that will not dissolve. You got me? If this makes sense to you, this is clear with you, give me a thumbs up. Any part of this is unclear, wave your hand around. So, sometimes the ion dipole attraction is stronger than ion-ion, and sometimes the ion dipole attraction is weaker than ion-ion. That determines if the substance is going to dissolve, and we'll look more into that next week. We have a whole unit on whether it will or whether it won't. Yeah?
So the ion dipole would be the chloride to the sodium, and then the ion-ion would be like...
Ion-ion is chlorine to the sodium. Ion dipole is...
the water to the...
Exactly. Water to chlorine, water to sodium. Capiche? Other questions? All right, off we go. Now, there's a special kind of dipole-dipole attraction that only occurs when when hydrogen is bound to a very electronegative atom. So if you have a part of a molecule where you have hydrogen, which is going to make a very electropositive area or a very low electronegative area, is bound to fluorine, nitrogen, and oxygen, bond. When hydrogen is having FON, we get hydrogen bonding. You can think of it as an upgraded type of dipole-dipole that occurs when hydrogen is bound to the three most electronegative atoms: fluorine, oxygen, nitrogen. FON. When hydrogen is having FON, your polar molecule gets upgraded into hydrogen bonding. Water is a great example. Water has hydrogen bonding because it's clearly a polar molecule, but hydrogen is bound to oxygen. So hydrogen is having FON. That polar dipole force gets upgraded to hydrogen bonding. Does hydrogen chloride have hydrogen bonding? Is hydrogen chloride polar? Yes. Is hydrogen bound to fluorine, oxygen, or nitrogen? No. So this would be an example of a molecule that has dipole-dipole, but not hydrogen bonding. Okay. If that's clear to you, give me a thumbs up. If you need me to repeat that, wave your hand around. It's perfectly okay. All right. So again, we learned dipole-dipole for polar molecules. We learned ion dipole when polar molecules attack ions. We learned ion-ion when the two ions are stuck together. And we just learned hydrogen bonding, which is the strongest polar dipole-dipole attraction. It's dipole-dipole upgraded. So this is a cool example of water. See, ice versus liquid water. So these represent water molecules. And the hydrogen bonding is why all life on this planet exists. And that has to do with water being less dense as a solid than as a liquid. In most cases, that's not the case. In most cases, with when something becomes a solid, it becomes more dense. The molecules get closer together. But with water, when water becomes a solid, liquid water becomes a solid, it becomes less dense. And it becomes less dense because of these holes, these gaps that form. Like you can see this big gap right here. What do you think is in that gap?
Nothing.
What's that?
Nothing.
Exactly. The lightest thing in the universe. Nothing. It's not air because air is oxygen and nitrogen. There's not enough room for air. There's just nothing there. So nothing is extremely light. So that makes the ice less dense and it can float in its liquid due to hydrogen bond. Okay, if you're with me so far, give me some thumbs up. If any part of this is unclear, needs to be repeated, wave your hand around. We're good, move on. Okay. So far we've been talking about polar molecules. Now there's non-polar molecules. And for that, I have paper clips. These are paper clips. You guys have seen these paper clips before. They're like, oh, I know, I recognize that's a paper clip. Paper clips are made out of metal. And you might know that metal can be magnetized. These paper clips are not magnetized. So it doesn't matter how hard I hit them, they're just not going to stick to each other. But if I bring a magnet and attach a magnet to a paper clip, then what happens?
Magnetized.
Then it's magnetic, and it can pick up other ones. So if I induce a magnetic field in this paper clip, that paper clip will behave like a little magnet. You've all seen this before a million times, right? It's not magnetic until I bring a magnet and I induce a magnetic field in it. Well, that's what happens in nonpolar molecules. Nonpolar molecules by themselves don't interact much with each other. And they certainly don't have intermolecular forces until they do. So what happens is a nonpolar molecule has a dipole induced into it. And that dipole propagates through the other materials. So you have a bunch of nonpolar molecules, they're chilling out, they're not doing anything, they're not interacting, but then something comes along and induces a dipole, basically makes the electrons pile up on one side, and that dipole spreads through the material. And that's what we say, a faint, temporary, induced dipole. To induce something is to make something else happen, make something happen in something else. I got in a fight, he induced me into that fight. Well, what really happens is the electron cloud gets polarized. The electron cloud that would ordinarily be pretty much spherical, all of a sudden isn't. It gets pushed to one side. Kind of like if you were to draw the electron cloud around this molecule, it would look a lot like this. Clearly not symmetrical. Well, nonpolar molecules, their electron clouds are symmetrical until they're not. So what does this mean? The larger the electron cloud, the stronger the London forces. By the way, it's not named after the city of London, it's named after a dude named London. So the larger the electron cloud, the more electrons get polarized, the stronger the London dispersion forces. All right, questions? Ready to move forward? Okay.
So what exactly is the London dispersion force? Like it makes it circular?
So you have basically a spherical electron cloud or just a symmetrical electron cloud. And then something comes along to pull electrons in one direction. Now it's not symmetrical anymore. You just created a partial negative end and a partial positive end. So that previously non-polar thing is slightly polar. And then that slight polarity induces another molecule, which induces another one, and another one, and another one. And the molecules become slightly polar and they'll stick.
Could that force that's inducing it just be like greater charged force? It's just like.
I'm sorry, my ear is totally plugged up.
I'm confused on like what's inducing it.
Something, anything. Could be the container. Could be a magnetic field, in fact. Could be an electric field. Something induces it to be temporary, to recreate a temporary dipole. Does that make sense?
Yeah.
Other questions? Moving on. So this is a great animation. You have a previously symmetrical molecule, something causes it to become polar, and this one induces a polarity into that. Boop. And imagine that goes on for billions and billions of molecules. It's just polar, 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 polar. It's extremely weak. It's extremely weak. Okay. If you understand this makes sense to you, give me a thumbs up. Any other questions before we move forward? Yeah.
If you took away the thing that was making them temporarily polar, would they go back to their regular state?
Yes. Others? Okay, so quick review of what we got so far. For similar sized molecules, and that's important because when the molecules change size, the rules basically get all cattywampus. But for similar sized molecules, if you're comparing molecules, the London dispersion force is going to be the weakest. Dipole-dipole is pretty strong. Hydrogen bonding is upgraded dipole-dipole. And then ion-dipole and ion-ion swap depending upon something you're going to learn next week. Sometimes ion-dipole is stronger than ion-ion. Sometimes ion-ion is stronger than ion-dipole. When you're comparing molecules, for similar sized molecules, weaker, stronger, strongest. Give me a thumbs up if you understand so far. Moving on. Now here's the thing. This is what we're going to talk basically for the rest of the class. Actually, 10 minutes, you'll have plenty of free time. The state of matter you have, solid, liquid, gas, depends upon how strongly the molecules are held together. If they have very high intermolecular forces, you're probably going to be a solid. If you have very low intermolecular forces, you're probably going to be a gas. So what we usually do is say, the higher the intermolecular force, the higher the boiling point, the higher the melting point. Because with molecules, there's always this competition between intermolecular forces and kinetic energy. We'll get to it in a second. Okay, so with your buddy, look at these molecules and determine with your best friend, is each of these molecules polar, non-polar, and if they're polar, do they have hydrogen bonding? Take a minute or two and look at these and determine what of the three, London, dipole, dipole, or hydrogen bonding, each of these molecules has.
Non-polar, non-hydrogen bonded,
That one, what about NH3? It's not hydrogen bonding, right? I mean, it is hydrogen bonding. It's not hydrogen, it's actually polar. Yeah, but it's still hydrogen bonding.
Polar molecule.
Okay, I'm off.
Wait, what? Yeah, I know. That one's polar, that's non-polar.
This is symmetric.
That one is.
Yes.
That one is not.
It's a 2-day month. So it's like
I don't say. I read that he's singing part.
I don't understand
So-
what it was like.
See how there's so this we didn't have this orange. Didn't have that orange. Pretty much everything is right here. So
They're looking at
yeah.
Okay, let's not so overcomplicated things. Don't you guys do that now? I told her, I just need to say like, no, mom, I'm gonna go here, you're ready to do it, so no. Like, wow, like, no. They were no. And they have the same amount of Jerry.
Okay, so let's do this. If we use 1, 2, or 3 fingers. If you think it's the weakest intermolecular force, London forces, give me 1 finger. If you think it's dipole, give me 2. And if you think it's dipole with hydrogen bonding, 3. Water, 1, 2, or 3. 3, 3, 3, 3, 3. Yeah, 3. Water obviously has, we talked about it, hydrogen bonding. Methane. What do you think? 1, 2, or 3? 3, 2, 1, 1, 2, 2. Methane is nonpolar. We have 4 identical bonds that all cancel out. Methane's nonpolar, so methane only has London dispersion forces. Look at PCl3. PCl3's got that fun little unshared pair right there. What do you think PCl3 is? 1, 2, or 3? 2, 2, 2, 2, 2. Yep. PCl3 is polar, but hydrogen's nowhere in there. Hydrogen's not having any fun, so it's just dipole. Methanol. What do you think about methanol? 1, 2, or 3? 3, 3, 3, 3, 3. Yep. This has hydrogen bonding. It's clearly a polar molecule, but the hydrogen is having fun hydrogen bonding. Nitrogen, the nitrogen molecule. 1, 2, or 3? 1, 1, 1, 2, 1, 1, 1, 1. Yep. Nonpolar, so only London dispersion forces. Argon. Don't hurt yourself. Yeah, one thing. It's argon has to be nonpolar because there's no bonds. And then NH3, ammonia. 1, 2, or 3? 1, 2, 3, 3, 3, 3. Yep. Ammonia is polar, and hydrogen is having fun, so hydrogen bonding. If you're comfortable with this so far, give me a thumbs up. Any part of this is unclear, raise your hand around. Okay. Now let's talk about states. So like I previously mentioned, states are determined by the competition between intermolecular forces that wants to hold the molecules together and kinetic energy that wants to make them scatter. Kinetic energy is movement energy. When you increase the temperature of molecules, what do?
Speed up.
They move around more, right? They speed up. We learned this back in 4th grade. So we call this the kinetic molecular theory. And it tells us all matter is made of particles that are in constant motion. And temperature tells us how much motion. Increase the temperature, more motion, more kinetic energy. Decrease the temperature, less motion, less kinetic energy. So water is a great example. If you have liquid water, there's a good balance between the intermolecular forces that holds them together and the kinetic energy which allows them to move. When you increase the temperature of the water, what are you increasing? The kinetic energy, till the kinetic energy is larger than the intermolecular forces and you boil. When you get that liquid water, put it in the freezer, you're going to lower the kinetic energy until the intermolecular forces are larger than the kinetic energy and the molecules are going to stick. They're going to be trapped together. Make sense? Questions? So the typical question is, which of these two molecules will have the higher boiling point? The one with the stronger intermolecular forces is going to require more energy to overcome their intermolecular forces. Right. So, just like we were talking about, with solids, the particles are fixed in a position, but they can still vibrate. A liquid, they are not fixed in position. They can move, but they're still stuck to each other. They can move over each other, they're still stuck though. Gases, the particles have so much energy, they don't stick together at all. They're just, bye-bye. If we were to look at you right now, if you were atoms right now, what state of matter are you emulating?
Solid.
Why do you say that?
Not doing
Because, yeah, you're not able to move. So you are currently emulating solids because you are fixed in position. You're not totally immobile. You're still moving around a little bit. You're vibrating, but you're fixed in position. When the bell rings, what material are you going to emulate?
liquid.
A liquid. You're still going to be constrained to the campus, but you're able to move around. Okay? Realize if you leave campus, you're violating chemistry. So you can't leave campus. You're still constrained to the flow of students in the building and the other building. You're still on campus, but you're able to move around. You're a liquid. And then at 250, what do you get to become?
Gas.
A gas. You get to separate and everybody goes their own directions. Moving on.
Yes.
Okay. So let's summarize what we've learned so far. The single strongest bond we have is the metallic bond. It's crazy strong. You never put some I gotta put a block of copper in the water and see the copper dissolve. It might react eventually, rust, but it's not gonna dissolve. Metallic bonding is extremely strong because of the electron C model. Then we have ionic bonded salts. Positive ion attracted negative ion. Sometimes that's extremely strong too. Sometimes it isn't. Then you have ion dipole, where with a polar molecule attacks the ion. If it's strong enough, it'll pull the lattice apart. So these two guys swap. Sometimes this one's bigger, sometimes this is bigger. And we'll learn why next week. Or you can look on the few slides down. And then polar molecules with hydrogen bonding are the strongest intermolecular forces. Then you have just plain old dipole-dipole, and the weakest for similar sized molecules is London dispersion forces. All right, how are we doing? Questions so far? Yep. Comparison, and then we're done. So you have a couple of these multiple choice questions on your test, and it's just, of the four molecules, which one has the strongest or weakest intermolecular forces? In this case, it's saying which one's going to have a higher boiling point. That means which one has a higher or stronger intermolecular force. Chat with your neighbor, take a minute and chat with your neighbor between chlorine and fluorine. Which one's going to be stronger?
Chlorine.
Okay, if you think chlorine has stronger intermolecular forces, point that direction. If you think fluorine has stronger intermolecular forces, point that direction. Interesting. Huh, one of you got it right. These are nonpolar molecules. And when it comes to nonpolar molecules, the bigger the electron cloud, the bigger the London forces. So Chlorine is atomic number 17. It has 17 electrons in the electron cloud. Fluorine's atomic number 9. It has 9 electrons per atom in the electron cloud. So 34 here, 18 here. This is 34 electrons that can be polarized. So the chlorine has more polarizable electrons. So it's going to have stronger London forces. If you understand that now, give me a thumbs up. If any of that is unclear, needs to be repeated, raise your hand. Okay. Specific question, just want to go over it again.
Yeah, can you just like.
Yes. So if your molecule is non-polar, which it clearly here is because that's a non-polar bond. The only bond present is a non-polar bond. So that's a non-polar molecule, and that's a non-polar molecule, which means we have London dispersion forces. London dispersion forces work on polarizing an electron cloud. So the bigger the electron cloud, the more polarizable the molecule is. Chlorine, being atomic number 17, has 17 here, 17 here, 34 electrons in the molecule. Fluorine has 8 or 9 and 9, so 18. So chlorine has more polarizable electrons, so it's going to have a stronger London dispersion force. Make sense? Other questions? Number 2. Hopefully with what I said right now, you know what this is. So point that way if you think it's ethane, that way if you think it's methane. Yes, it is ethane. They're both nonpolar because all the electrons, all the bonds cancel out. That's a nonpolar bond, and then down, 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 up, down, left, right. Those all cancel out. Up, down, left, right. Those cancel out. 2 nonpolar molecules. Ethane has more electrons, so ethane is going to be more polarizable. So it's going to have stronger London dispersion forces. Both of you realize that's the case for argon also. Yeah. Okay. Cool. So those are all nonpolars. Here's a mix. Now you have a mix of polar and nonpolar. Take a look. Take a minute and decide with your friends which of these two has stronger intermolecular forces.
Yeah, literally.
I feel like we haven't had St. Patrick's Day in 4 years. When is St. Patrick's Day? Isn't it in March?
I literally remember we had it in 2 years. 8th grade, we were all
Sounds good.
It's
in March. March or April. Mr. Byers,
Yes,
is St. Patrick's Day in March?
I think so.
It's March 17th.
There you go.
No, it's the 22nd. Yes, it is.
Anyway, so speaking of that, if you think carbon dioxide has stronger intermolecular forces point that way, if you think water has stronger intermolecular forces point that way, what do you think? Yup. Water is polar. Carbon dioxide is non-polar. Water has hydrogen bonding. Carbon dioxide has London dispersion forces. At room temperature, that one is a liquid. That one is a gas. Remember, stronger intermolecular forces, closer to solid. This guy. This is methyl chloride, and this is methane. What do you think? Yep. Non-polar, polar. By the way, does this have hydrogen bonding? No. It has hydrogens, but those hydrogens are not having fun. So dipole, London. And then NH3 and PH3.
No.
What?
This one's polar.
Bigger.
This one's polar. But this one, hydrogen is having fun. This one, hydrogen is not having fun. So they're both polar, but this one has hydrogen bonding. Ah, yeah. Learning. Yeah. And that's where we stop. Okay. Any questions before we quit?
No.
Can we,
Yes.
can you explain that?
Number 3?
Yeah.
Sure.
Having
You've
fun.
got two molecules that are both polar.
Like this.
So dipole, 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 dipole.
I don't know if it's.
But in this case, the hydrogen is bound to fluorine, oxygen, or nitrogen. So the hydrogen is having FON. So its dipole gets upgraded to hydrogen bonding, which is the strongest form of dipole-dipole.
Oh, okay.
Comfortable with this?
I know we have Rick.
All right. Other questions? Cool. You got like 10 minutes to work on your video guide, work on other worksheets, take a nap, don't care, whatever.
What do you know what they do?
Remember since we're good.